everyone, today we are diving into the buffer overflow attack using the Seed Labs environment. First we need to download the zip file of the lab setup and we need to extract it so that we can observe two files in the lab setup folder, that is code and shell code. We need to open the code folder in the terminal and we can observe the stack C program with vulnerability of string copy function. So a string copy function is a vulnerability because it does not check the boundaries, allowing us to override the return address on the stack, which means by injecting more data than the buffer can hold, we can hijack the instruction pointer to point our malicious shell code. That means we can write the program of the root. So the goal of the level 1 is that to master the fundamentals of hijacking the instruction pointer. In this we have a 32-bit system with a known buffer size. So in that we need to replace the shell code with our 32-bit. The shell code, we can find the code for the 32-bit. We need to copy this and paste it in our exploit.py file. And to run this we need to disable ASLR and stag out with this command. So this command is used to disable the address based layout randomization, that is by setting it to 0 memory static. So address is found in the, so by using this command we are changing the secure shell to dash to ZZ. To execute the exploit.py we can use this command, and to find the buffer size we have to go to the GTP terminal by using the command. So here we can find out the vulnerability of the stack, and to pointer the values we use these commands. These are the pointer values for the offset value. We need the difference between here. We got the offset value of 108. And we will use this offset value in the exploit.py by increasing into 4 bytes, and the return address will be change the return address. We can increase it to overcome the stack value and to execute our shell code. Now we are going to run the exploit.py file. And we need to run our stack. Here we also need to change the start point because we have to overcome the return address, and start point should not be at the loop. And we'll run it again. So here we can see that EUID is 0 and we have the root access. So this is level 1. Similarly for level 2, the goal is to learn how to succeed when you don't know the exact buffer size. So we will almost apply all the logic, but we have no idea of the buffer size. So here we make small changes in the exploit.py file, that is we have no idea of the buffer, so we comment out our start point and remaining values are almost set. And we comment out the offset because we don't know about the buffers. So now we will run this file. So here we successfully overcome the level 2 and we can verify it by same method, and we have the root access. So for level 3 the primary goal is to overcome the null byte constraint of 64 bits. So for level 1 and 2 we mostly use 32 bits, so here we will use the 64 bit. So using the same method we replace the 32-bit shell code with the 64-bit shell code, and the start point would be the 570, which is the exact bytes of the bad file minus the length of the shell code. We'll make some changes in the offset, and it is 64-bit. We'll make the L equal to 8 and this value changes based on the output. Now we will run the file. Here again, level 3 is successful, we can verify, and we have the root access. For level 4, the level 4 goal is to execute an attack and the buffer is too small to hold the payload, that is the buffer is tiny. For example 10 bits, you can't fit a shell code inside a 10-bit code. So for that here we made small changes in the return address and the offset based on the goal of our level 4. So we, as you can see, we can have the root access and we overcome the and we achieve all the goals of the 4 levels. Thank you.